When a good electrical conductor like copper or aluminum is exposed to a changing magnetic field, a current is induced in the metal, commonly known as eddy current. A strong magnet can induce eddy currents, creating electromagnetic forces within the metal like aluminum or copper, which are not ferromagnetic. We are having a demonstration here, dropping a magnet into a metal tube. Here we have taken a copper metal tube and a magnet is dropped into it. As the magnet drops through the tube sees a changing magnetic field. This changing magnetic field induces a current that circles around the tube. That is, a current going around in a circle like that creates a magnetic field. The magnetic field created by these currents of electricity, the current going around in a circle like that creates a magnetic field. The magnetic field created by these currents of electricity is in the opposite direction of the magnet's magnetic field. The magnetic field created by the eddy current opposes the magnet's field, while the gravity pulls the magnet down. The eddy currents create a magnetic field that resists the motion. Hence, when you are dropping this magnet through a copper tube, it comes with less than the acceleration due to gravity, because there is a resistive force is acting on that. Sometimes it may come with a constant velocity also, because there is an opposing force in the upward direction, the gravitational pull is in the downward direction, with the net force is coming down. If these two are balanced, then it comes with the uniform velocity sometimes.
Yeah, in this experiment, we are going to demonstrate the Lenz's law. Whenever you talk about Lenz's law, you have to think about the electromagnetic induction. In electromagnetic induction, the EMF is induced by the movement of the magnet through a non-magnetic material, coil made up of non-magnetic material. Whenever you take a substance and then drop it to some height, it has some potentiality. It gets attracted towards the ground because of the gravitational force. Let us see how does it behave. When I leave this is the simple cylinder made up of brass, which is non-magnetic material. The moment I leave it, it just goes to the ground without any under the influence of gravitational force. Now let me check whether it is going to behave in the same manner when I drop it through this tube. This is a copper tube made up of this copper tube is a non-magnetic material. Now this tube can be visualized as a coil of copper wire wound continuously from one end to the other end. Then when you draw the brass cylinder through let us see whether there will be any change in the transit time when this magnet is dropped through this tube. This is the neodymium magnet. When I drop this, I am leaving the magnet. Now, you see what's happening? It is still coming. Still in the process of traveling through the tube. The transit time is increased. This is a copper rod and this is a magnet. So we are dropping into this one. Previously we dropped a non-magnetic material, nothing happened. It is very similar like any freely falling body. But in the case of this magnet, what's going to happen? Just to verify. Let's watch this. Yeah. See, oh great. It's moving very slowly into the copper rod. Yes. Now let us try to reason it out. What is the reason for this magnet to travel slowly in the copper tube? We know that whenever there is a change in the flux, magnetic flux lines, the EMF is generated whenever the magnet is made to move through the coil of wire. Magnetic field flux changes those change in the flux lines will induce the EMF in the coil. Whenever there is an EMF, the current is also there. Induced current will, along with the current, magnetic field is generated. So now you have two fields. One is the magnetic field, the other one is the weight of the magnet, which is trying to pull the magnet towards the earth, whereas magnetic field will try to push it up. So the resultant force will be the greater one. The weight of the magnet being more than the weight of the magnet, is more than the magnetic force. The net force is the difference of the two, and this has made the magnet to travel slowly through the tube, and eventually it has come out. And this tells you that whenever there is an induced EMF, induced current is generated. The induced current will act in the opposite direction to the process which is taking place. Now, what is the process? The process is the magnet made to fall under the influence of gravity. The induced current is generated that tries to lift the magnet up and then push it up. Weight of the magnet will try to push it down. The resultant of these two forces will be acting towards the greater force. The greater force being the weight of the magnet, it is traveling through this, and then that has increased the transit time of the magnet traveling through the tube when compared to normal.
We have some of the examples. In automobile speedometers, we are using these eddy currents. Magnetic brakes, energy meters, induction furnaces, free fall devices, that is detecting coins in the vending machines, galvanometer, a device which measures small electrical currents. The eddy current testing is a non-destructive testing. So without destructing that, we can calculate or we can measure the testing using the eddy currents.